Hey, it's Dr. GB, going to walk you through the answers to the equilibrium quiz. All right, so looking at the first question about ammonium hydrogen sulfide, how does the H2S, or the hydrogen dihydrogen sulfide concentration, how is it affected by any of these things? So the first one is what happens when we remove NH3. So if we remove NH3, what's going to happen is the reaction is going to shift to the right to replace it, and by going to replace it, it's going to increase the amount of H2S relative to before we started. So the amount of NH3 is going to, or H2S is going to increase. Now, if we add NH3, we're going to have the opposite effect. Because if we add NH3, we're going to have more reactants than, more products than we should. So the reaction will shift to the left to counter that. And so adding NH3 is going to decrease our H2S production. Now, looking at this question, your first instinct may be, oh, if we increase NH4HS, we shift to the right to dilute it, or excuse me, if we remove some NH4S, we shift to the left and decrease our H2S production to accommodate. However, there's a really important fact here, and that is the fact that our NH4HS is a solid. And so that means that removing it will have no effect on the production of H2S because it's not a part of the equilibrium expression. Now, increasing pressure to the flask by increasing helium gas, this is also going to be a no effect. And finally, decreasing the volume by increasing the pressure. So if we decrease the volume, our reaction is going to shift to the side with fewer moles to maintain the equilibrium pressure. And so what's going to happen is that's going to decrease our amount of H2S as the reaction shifts to the left towards the reactants. Okay, the second one is the Born-Haber process. So it's asking you, so you are an industrial chemist and you want to increase the efficiency of production so you can make more NH3 from the same amount of H2 and N2. So we can't change the volume of our container and we can't afford to purchase more H2 and N2. So how can we change production? So right off the bat, I want to say that some of y'all said increasing temperature because increasing temperature would increase the reaction rate. And so if you said this, you got 4 points. Because your answer isn't incorrect, but it's not the angle that I wanted you to take. I wanted you to address this from the perspective of Le Chatelier's principle. So I gave you a negative delta H here. This means the reaction is exothermic, and that means heat is a product of the reaction. So if we increase the temperature, we increase our heat. If we decrease our temperature, we decrease the heat. And so what we want to do is we want to manipulate, if we want to increase our NH3 production, we're going to want to manipulate the amount of heat that we have to cause the reaction to shift to the right so we make more NH3. And so if we were to raise our temperature and increase our heat, the reaction would go towards the reactant, so that would not be the way to handle it. If we were to decrease our heat, that would cause the reaction to shift to the right towards the products and make more NH3. So we would want to decrease the temperature to push the reaction to the right. Now, for those of you who came at it from the approach of kinetics, this may seem counterintuitive. And so this comes at a really important crux of actually what's going to be wrapped up nicely in our last section. And that kinetics, equilibrium, and thermodynamics are all part of what make a reaction go. They are related to each other, but they are not the same and they have different considerations. So in this case, this is where you would have equilibrium and kinetics working against each other. So if you increase the heat, you increase the reaction rate constant, but you decrease the equilibrium and you disfavor your products by increasing the heat. All right, so these are things that like chemists and chemical engineers have to think about when they're making chemical reactions happen on a large scale. Okay, so the next question is about about a process that makes the H2 that goes into the Born-Haber process. So you have this chemical reaction here where CO plus H2O forms CO2 and H2. And you need to find the K, what is the partial pressure of each two at equilibrium, and what is the Kc? So we can use the Rice equation to approach gases. It's just instead of using concentrations, we're going to use pressures, alrighty? And so the way we could do that is we start up our Rice equation. So you've got R, I, C, and E. So initially we have 2.00 ATM of CO and 2.00 ATM of H2O. We have no CO2 and no H2. So what we're going to do is we're going to take some amount X, we're going to subtract it from CO and H2O and add it to produce CO2 and H2. So at equilibrium, our CO and our H2O are both 2 minus X, and then our CO and our H2 are both X. So we're given here the Kp. Alrighty, so this is the equilibrium for pressures. So 10 is equal to X squared over 2 minus X. Now you may be like, Dr. GB, we have to go and we have to spread that out. What you can do is or 2 minus X squared, because we have a squared on our top and the bottom, we can take the square root of both sides. Alright, so we get the square root of 10. Okay, so we have 3.16 is equal to X over 2 minus X. All right, so 6.32 minus 3.16X equals X. X is equal to 1.5. So the partial pressure of H2 at equilibrium, alrighty, is going to be 1.52. So at equilibrium, H2 is equal to CO2, which is equal to 1.52 ATM, and CO is going to be equal to H2O, which is going to be equal to 2 minus 1.52, which is equal to 0.48 ATM. Now, the next question becomes, what's the relationship between our Kc and our Kp? So, the Kc is equal to the Kp times R times T to the delta N, where delta N is the change in moles. And so the thing about this reaction is on the left, we have 2 moles. On the right, we have 2 moles. 2 minus 2 is 0, so delta N goes to 0. And so when you have something raised to the 0, it goes to 1. So in this case, Kc is going to be equal to Kp. So Kc is going to also be equal to 10. And that brings us to our last problem, which is arguably the most complicated problem, and this is the antimony problem. Okay, so what's going on here is we have this chemical reaction here where solid antimony sulfide is added to hydrogen gas to make solid pure antimony and then hydrogen sulfide gas. Colloquially, we refer to this as hydrogen sulfide, but I guess technically it's dihydrogen monosulfide. Now, what this reaction is saying is we have a vessel that contains a volume of 2.5 liters, all right? We add together 0.01 mole of antimony sulfide, alrighty, and then we add in H2 gas, all right, so that's 0.01 mole H2, okay? So what happens is those two combine to make pure antimony, but then they also produce H2S. Now, here's the deal with H2S. If we want to figure out what our yield is, we can't measure H2S gas because it's a gas, all right? So what we want to do is we want to convert H2S into something that we can measure, either a solid or a liquid. And so the way that we achieve that is we get another like little jug thing, okay? And we fill it with liquid water. That H2S is funneled over into water where it then dissolves, all right? And so what happens is you have H2S aqueous in the water. Now we've just taken our H2S and we've put it in water. We still really can't measure that. So what happens is we take H2S and then we add in lead nitrate. All right, so that's PbNO3 2. Now, anything with a nitrate is going to be soluble. So this is actually Pb2 plus plus 2 NO3 minus. What happens here is that Pb2 plus is going to kick off the hydrogen. So our products are going to be H2 gas plus PBS plus 2 NO3 minus. So if we were to write our net ionic equation, we would actually get rid of the nitrate, and then we would have H2S plus Pb2 plus makes H2 plus PBS. Now, this is a gas that either, H2 is either a gas that means dissolved in the water or it bubbles off as a gas. PBS is a solid, and so we are told that we have 1.029 grams of PBS, all right? So what happens here is we take our grams of PBS, so we have 1.029 grams of PBS. We convert that into moles, all right, and we divide 1.029 divided by 239.2, we get 0.0043 moles. Wonderful. Okay, so that is our moles. So here's the deal. If we look at this reaction over here, all right, we have 0.0043 moles. But what we want to know is we want to know how much H2S we've produced. So to get there, we have to go from moles of PBS to moles of H2S. And it turns out that there's a 1 here in this reaction and there's a 1 here. So we can use stoichiometry to convert from one to the other. So 0.0043 moles of PBS times 1 mole of PBS per 1 mole of H2S, all right? That gives us 0.0043 moles of H2S. Great. So we know how much H2S has been produced as a product of this reaction over here, assuming we haven't lost any. So that brings us to the question, what is the equilibrium concentration? So this amount here is the amount that is produced at equilibrium. All right, so this is our X in moles. All right, so if we want to find the equilibrium concentration, what we can do is we could take 0.0043 moles and we divide it by 2.5 liters, and that gives us 0.0017 molar. Wonderful. Okay, so then that asks us the question, okay, what is the equilibrium constant? So this is where we have to set up our race table. Alrighty, so we want to start by converting moles into molarity. So 0.001 mole of antimony, we take 0.001 divided by 2.5, that gives us 0.0004. Oops, I'm off by an order of magnitude, y'all, I'm sorry. 0.01 divided by 2.5, that gives us 0.004 molar. All right, and then we have 0.004 molar here. Okay, so we have to set up our race table now. So if our reaction, so again, we've gotten what we need out of here, which is the moles of H2S, and now we have to go back to our initial flask. So our initial reaction is Sb2S3 solid plus H2 gas goes to form, and that is, okay, 3H2 actually, goes to form 2Sb solid and then 3H2S. Okay, so to find this, we have to figure out our concentrations of H2 at equilibrium, because we know, because we're not going to know Sb2, S3, and then Sb in our equilibrium. We're not going to include that in our equilibrium expression because they are solid. So what we're going to do here is we know that at equilibrium we have 0.0017 molar of H2, or excuse me, of H2S, all right? Now, we know initially we started off with 0.004 molar of Sb2S3 and then 3H2, all right? Now, again, we're going to ignore Sb2S3 because it's a solid. So we know that we're going to have some amount X that we're then going to add to H2S to get to our equilibrium. Now, we know since we have a 3 here, it's going to be plus 3x. And then over here on the left hand, we know it's going to be minus 3x because of the 3. So what we can do is we can solve for x. 3x is equal to 0.0017. X is equal to 0.0017 divided by 3. Alrighty, that's going to give us an x of 0.00057. All right, so our equilibrium is going to be equal to 0.004 minus 0.0017, which is equal to, alrighty, so that's 0.0023. And if we set up our equilibrium constant, that is going to be equal to 0.0017 to the third divided by 0.0023 to the third, which would be 0.404. All right, so looking back, this number is a little bit off, but we're not going to worry about it. So it's 0.43 versus 0.404, but close enough. Alrighty, so then the question becomes, how do we know what mass of pure antimony would have been present in this flask? So this is just a matter of stoichiometry. So we don't include our solids in our equilibrium expression, but what we can do is we can use our stoichiometry for the reaction to determine this. So we know that our chemical equation for this reaction is sp2s3 plus 3H2 gas goes to form 2Sb solid and 3H2S. Okay, so this is asking the question how much pure antimony is in the flask. So what we can do is we know that at equilibrium, we have 0.0017 molar of H2S. So what we can do is we can convert this back into moles, all right? So 0.0017 molar times 2.5. Alrighty, that gives, 0.0017 times 2.5. And it gives us 0.00425 moles of H2S. Now, we know we have 0.00425 moles of H2S, all right? And we have 3 moles of H2S for every 2 moles. So 3 moles H2S for 2 moles of SB. And then we multiply by the molar mass, so 1 mole. And then the molar mass of antimony is, and I can't remember off the top of my head which it is, so I'm going to have to use the ptable.com. Bear with me. Alrighty, 121.76. 121.76 grams per mole. So times 3 divided by 2 times 121.76. Okay. Okay, I answered it wrong in my calculator, so it's times 2 divided by 3 times 121.76. That would be 0.362 grams, or the answer that I have on Moodle will be 0.349. So I'm a little bit off. My numbers got off somewhere, but it would be around 0.35. All right, would be the answer. So I'm 0.35. Alrighty, so that's how we would solve this problem. I'm happy to answer any questions if you've got them.